How autonomous racing planning works? The answer in 6 minutes.
An autonomous vehicle, also called self-driving car, is defined as a vehicle capable of driving by itself through unknown scenarios by dealing with external obstacles in the environment. This is composed by a net of passive and active sensors to capture the scene and vehicle status. Among them, we find encoders, GPS systems, inertial measurement units, lidars, and radars. In addition, a set of servo actuators are powered to generate the appropriate motion, such as electric motors, braking, and steering systems. At this point, the main computer, acting as the vehicle brain, processes all the sensor data to identify the environment and localize the car relative to the current scenario. With this information, the planning stage computes the proper trajectory that finally the controller will be in charge of following. However, despite of the multiple things that may be explained here, in this video we are going to focus on trajectory planning for racing driving.
So, first of all, let's see what trajectory planning means. The main idea behind planning is to compute trajectories to properly guide the car between 2 points and through complex scenarios like, for example, intersections with other cars and pedestrians, or lane changes in highways, ensuring certain levels of safety and dynamic feasibility. However, difficult driving scenarios such as crossing pedestrians in prohibited roads are extremely complicated to predict, and current available techniques are not able to handle them. Here's why autonomous racing planning comes up exploiting extreme vehicle capabilities to compute safer trajectories in those complex scenarios. Autonomous racing planning consists on computing the road that makes the vehicle to perform as fast as possible by handling extreme dynamic behaviors like working close to the tire adhesion limit in order to maximize the tire road power transfer. The most evident usages are autonomous driving competitions like, for example, Robo-Race, F1/10, and Formula Student. However, there is something beyond competitions where racing planning can be used for. Autonomous racing planning can help in normal driving environments by providing fast solutions to difficult problems, like, for example, avoiding unexpected obstacles crossing the road. Solving the planning problem on such complex situations requires a deep enough knowledge about vehicle dynamics and, in consequence, its extreme capabilities. In this robotic automotive application, the bicycle model representation is commonly used so that the car is actuated by varying the quantity of linear acceleration in the rear wheel and the steering angle at the front wheel to produce motion. Using the Newton's second law, we can express the vehicle physics as a set of differential equations. An important variable in racing scenarios is the slip angle. This is defined as the angle between the orientation of the tire and the orientation of the velocity vector of the wheel. With this dynamic model representation, we obtain the velocities based on some inputs, but we want to obtain also kinematic variables. To do so, a curvature error-based representation is introduced to compute lateral and orientation errors with respect to the road center line. In the following, this model will be used by the principal algorithm to compute the racing-based trajectories. At this point, we are going to take a look to some important aspects in racing driving. The first to consider is the front and rear slip angle status. If the vehicle has a front slip angle greater than the rear slip angle, then the car is in understeer behavior. By contrast, the vehicle will be under oversteer situation if the rear slip angle is greater than the front slip angle. In addition to this, the higher the product of linear and angular velocities, the more extreme racing behavior. Driving as a racing driver requires of some previous knowledge of the track and the vehicle. In this case, we will need to know the following: the curvature of the circuit at every point along the center line, the width of the track, and the car dynamic parameters. The constrained optimal base approach is a promising technique for autonomous racing planning since it allows to minimize the racing time subject to some constraints like the dynamics of the car, road limits, obstacles along the track, and maximum admissible values of physical variables of the car. Hence, this algorithm minimizes the total lap time by applying optimal values of steering and acceleration to the bicycle equations that makes the car to evolve in time, fulfilling the imposed constraints and providing the optimal trajectory throughout the track. Thank you for watching, guys, and keep racing.